Yeah, just and it. So in this talk, I'm going to talk about a solution to achieve a zero carbon scenario in the future. So here we focus on the transcontinental power pool. So what's a power pool? It's interconnected power grids that span across different countries. So by this power pool, actually we can achieve a zero carbon emission in the future. And this research we published just a few months ago in Nature Communications with our co-authors. So in achieving a zero carbon future, we have to rely on renewable energy. But there are a few challenges in that. The first one is that the renewable energy, they are unequally distributed across space. So this figure shows the power of solar across the world. You can see that in Europe, there's very low energy for the solar power, but while in Africa, there's lots of energy. So this also applies to wind. So the renewable energy, they are just unequally distributed across space. And also there's a temporal variation. So we don't have a controller to control the weather. Sometimes there's wind, sometimes there's no sun. So this becomes another challenge for the low carbon future. So what else we have? We also have land constraints. If we think about the small islands, the small size countries, these countries don't have land to install the solar panels, to install the wind turbines. And also the forests, they have captured so much carbon dioxide, so you cannot cut down forests to install the wind turbines and the solar panels. And also, even if we have much sea, but we have the MPA, right, marine protected areas, you cannot install wind turbines on the sea. The fishermen will not agree with us. So we have to talk about three challenges here. So how can we solve this? Right, there should be one solution that can address all these three challenges. That's why we can have an idea about the transcontinental power pool, which is possible to address these three challenges. So here is a map showing that how Europe, they are planning to connect each country by their transmission lines. So just imagine if we have low quality renewable resources, what's the solution? Import from other countries. So what happens if your wind is not blowing? Import from other countries. What if we are small size countries, just import from countries which are very large in size? So by this power pool, we have the potential to address all the challenges we mentioned before. So the problem is that what's the cost to build this power pool, and to how much extent can it achieve a zero carbon emission scenario? In our research, we imagine that in 2050, we are going to achieve a zero carbon electricity system. We have developed two scenarios. First, there is no power pool, which means countries, they are not sharing renewables with each other. The second scenario, we are building transmission lines, which means that countries, they are sharing renewables with others, so there's trade between each countries. The question also asks is that how much demand can be met by only renewables, and what's the change in the cost of this system? So in our research, we only include the renewable energy, which has a solar PV, rooftop PV, and concentrated solar power, onshore wind, offshore wind, and hydropower. We also include short-term storage systems like battery and hydro pumps. So we have a very simple framework here. Our input is the renewables and battery. And we only use the top 10% land for the renewables. And our goal is to achieve a zero carbon electricity system. And then we use our power system planning model to simulate what is the capacity and operations of our renewables. So here we have classified the world into 6 power pools. On the left, this is the North American power pool, which includes Canada, USA, and Mexico. And then it's the South American power pool. And the third one is the European, North Africa, and Middle East power pool. And the fourth one is the Sub-Saharan African power pool. And then this one is the Russia, East Asia, and Indian power pool. The last one is Australia and the Southeast Asian power pool. So here I show our results. So first, let's look at how much demand can be met by the renewables alone. So here, each color means the demand shortages. If it's in darker red, means that more demand cannot be met by renewables. If it's in lighter yellow, it means that less demand, more demand can be met by the renewables. Here you can see if you are not sharing renewables. Here in the Southeast Asia, Indonesia, more than 20% of demand cannot be met by renewables, which means there's 20% demand shortages. And in India, it's about 10% to 20% shortages in demand. In Europe, you can find that there's about 5 to 10% shortages in demand. So this is a very big issue, right? So what if we can build a power pool so the countries can share their resources? Well, we find that all countries they can achieve zero carbon emissions while meeting all of their demand supply, while meeting all of their demand by only renewables. So we are not only looking at the demand, we also care about cost, right? We don't want to pay high bills for our electricity. So here, this is a case where we are not sharing the renewables. You can see that in Europe, to pay 1 megawatt hour of energy, we are paying like more than $90. And in Asia, we can find that we are also paying like $70 for one megawatt hour of energy. And we can find that in South America and Africa, they have somewhat lower cost for energy production. So what if we build a power pool? So here in one power pool, all countries, they are sharing the cost. And the cost is the same for every country. So first, let's look at the North American power pool where we live right now. So because America have large amounts of energy, so actually it can supply the demand by itself. But if we build power pool, we can see there's a slight decrease in our cost. And while Canada, as an exporter, can have a slight increase in their cost. And if we look at South America, what we can see, although the cost is low in South America, but by building power pools, the cost is still lower than before, right? Before it's about $40 per megawatt hour, and right now it's around $30 per megawatt hour. And the largest beneficiary is in Europe. So before we build power pools, it's around $90 per megawatt hour. But after we build power pools, the cost decreased to around $60 per megawatt hour. And this cost is called the import energy from North Africa and Middle East. And for sub-Saharan Africa, they all, by sharing resources, they also have a decrease in their cost. And in East Asia, you can find that Russia, they have an increase in their cost because they are exporting energy to these Asian countries. So they have an increase in their cost. But countries in Asia, they can have a decrease in cost. And in Southeast Asia, we can find that Australia, they have an increase in their cost because they're the major exporter to supply energy to the Southeast Asian countries. So the whole conclusion is that by building power pool, we can reduce the cost in every country. So here I explain more why the cost will decrease. In the first column, it shows the cost when they are not sharing renewables. And in this column, it's the cost when they are sharing the renewables. Each color means the cost for each technologies. So here, by building a power pool, we will have less renewable energy cost. The cost for rooftop PV will decrease because that we can use the high quality resources from other countries, so we don't need to build that much renewable energy. Of course, we need more cost to build transmission lines, but this cost increase is much lower than the cost decrease from the renewable energy. So our conclusion is that even with very tight land constraints, our power pool can achieve a zero carbon emission energy system, and also with lower system costs. And we are thankful for our collaborators and our lab members. Thank you.